Okay, so good morning, students. Okay, so in the last class, okay, in the last laboratory class, we were discussing regarding the particular MATLAB experiment. Okay, so I'm thinking of completing this particular topic today. Okay, so that from the next class, since this PID controller will be completed, so from the next class we can start with the new topic of board plot. Okay, so I will be teaching you the topic of board plot, and Principal Sir will be teaching you the Nyquist plot. Okay, so that is why I will be completing this portion in today's class. Okay, of the PID controller. Okay, now in the last class we have seen that the regular suppose a normal system, okay, of this transfer function, that is 1 by s square plus 10s plus 20. So if one unit step input is given, then the output response will be like this. Okay, where we have seen that there was almost 95% error. Okay, so 95% error was there is a power cut. Hello. So actually there was a power cut, so my network got disconnected. Okay, so I've again connected with my hotspot. Okay, so as I was discussing, that in the last class, we have seen that when a system, okay, of a second order system was actually this a unit step input was given, then the output of that particular system was having 95% error. So in order to minimize that error, okay, we have used a proportional controller. So the proportional controller, what it did, it increased the magnitude. Okay, so a gain of 500 was taken, so it increased the magnitude, and the output was a typical second order system where we have got some overshoot. So magnitude has increased. So the input was one unit. Okay, it is a unit step input. So the input is having a value of 1. So the output which we got, it was very close to 1. So previously it was 0.05. Now it is close to 1, but there was an overshoot. So overshoot means there is oscillations. That is why the settling time was too much high. Okay, so now PD controller was used. With the help of PD controller, which is the proportional plus derivative controller, we were able to minimize the particular you can say overshoot. So the settling time was reduced. Okay, so the settling time was reduced. But what was the problem? The problem was that the steady state error, so error was not 0. We were having some error. So the overshoot, you can see it was reduced, but with the overshoot the oscillation damping was done, the settling time was reduced. Okay, but the steady state error was not 0. Okay, so next we will use PI controller. Okay, so this was the conclusion that as I've told. So with the PI controller, okay, that is the proportional plus integral controller. That means we are connecting a proportional controller along with that an integral controller. So it is not generally represented like this because this is a mathematical just an equation we have written, Kp plus Kis, where Kp is the gain of the proportional controller and Ki is the gain of the integral controller. But actually the representation is like this. Okay, Kp, Ki and Kd are placed parallel and their summation is added over here. Okay. Okay, so the summation is added. So as a result, now you can see the input to the plant is US. Okay, so error multiplied by the proportional plus integral controller transfer function will give you the US. So UT is represented as it is Kp Et plus Ki integration of Et dt. Okay, so now after Laplace transform, you can see this is the transfer function Cs, that is US by Es. Okay, that is the controller transfer function is Cs, which is US by Es. It is Kp plus Ki by S. Okay, so now as you know that the closed loop transfer function will be Xs by Fs. So Xs by Fs will be this one, Cs into Ps by 1 plus Cs into Ps. Okay, Cs into Ps, because this is Cs, this one is Cs. Okay, so the closed loop transfer function will be Xs by Fs, which is equals to Cs Ps, which is the forward part transfer function, open loop one, plus Cs into Ps. Now if you solve this, if you put the values, okay, of Cs over here and ps as it is. Ps value we all know that 1 by s square plus 10s plus 20. Then if you replace them, okay, then you will get this transfer function, modified one. Now what we will do, we will, previously our gain was forward path the proportional gain was 500. Now we will reduce to 30. Okay, since in integral controller we don't use too much proportional controller, that also we can see, we will just tune it, we will check. So here we have replaced with 30 and 70. The integral controller gain is 70. Okay, so now replacing these values, we get this particular transfer function. Now this is our actual transfer function now. Okay, and into this transfer function we will give the step input. So xs by fs. Okay, so fs will be now the input. Okay, so input will give this, we will provide the unit step function. So for the MATLAB code, what we will do, we will just input kp, change the value of kp and input ki, and then write the same thing, PID, we will write kp and ki. Because in PID function we know first one is the proportional controller, next is the integral controller, next is the derivative controller. So, okay, since we are not using derivative controller, so we will only use the first. So MATLAB will understand that we have used PI controller. We don't need to put 0, comma 0. Okay, so let us do this. So previously what we have seen, we have done the case, this is for the P controller, this is for the PD controller. Okay, so now what we will do, we will hide this because we don't want to plot first the step function over here. Okay, we don't want to plot them. Okay, so KD, let the MATLAB program save the value of KD. Okay, but if you are not plotting the step, then it will not show. But if you want to process them, there is no problem, they can continue. Okay, so now in our case, okay, this, I will also hide this one. Okay, for the first time. Okay, then we will also unhide them and see, compare them side by side all together, merge them. In our case, the plant transfer function is G. We have taken G. Okay, now this is the actual transfer function. Now the transfer function will be modified like this. So over here what we will do, we will copy this and just rename them as Ki. Ki is 70. Okay, Kp is, okay, we will put it 500. Let us see what will happen. And this one will be Ki. Okay, and this one will be Pi, since we are using PID controller, PI controller actually, Pi. Okay, and then we will use this step function. Okay, now we will let us run it. Initially it takes some time because it's, since it is doing running for the first time. Okay, wait, this one has to be this one has to be high hidden also. Let us try again. Now see, this is the actual transfer function, this is the transfer function modified after using the PI controller. Now since we have taken the gain to be 500, you can see too much overshoot is there. Because of the overshoot, it is not able to, stabilize, the system was stabilized, but error is not minimized. So it is not always necessary to keep the proportional controller too high. We can use 30 also. So let's see for 30. Now you see, since the proportional gain is less, so what is the problem over here? The problem is why we have not used 500. Can anyone say why we have not used 500? Why overshoot was there? Because in case of PD controller, if I do it once this time, okay, let me compare them. If I do this one, suppose I take 30 over here, I run this. Okay, you can see it is not reaching 1, it is reaching 0.6. It is reaching 0.6. So 30 is not enough. So if you use 500, then it is showing that it is reaching something like that. We can reduce it also to suppose 200 also. Let us see what happens. There also we can see it is, but the thing is the settling time, it is taking like 0.5 seconds. Okay, so let us keep it as 500. Okay, we are keeping this. Now what we will do, this is the PD controller. Okay, this is PD. Now we will compare this also. We will use this hold on for all the case. So hold on here also, here also. Okay, now if I want to run, suppose I close this part, I am running. Now the blue portion is for the PD controller. The blue is for the PD. Okay, but orange is for PI. So can you tell that why this PD is having less overshoot and PI is having more overshoot? Why? Anyone? Are you getting it? Are you able to understand? PD कंट्रोलर का ओवरशूट जो है वो कम है, PI का ज्यादा है. क्यों? ऑरेंज वाला PI है. Anyone, please? I think it should be answerable. Means you should be able to answer it. Anyone? I can see the name of Abhishek, Anisha. Can you hear?
Yes, sir.
So can you tell the difference? Why for the PD controller we are getting less overshoot, the blue line, and for the PI controller we are getting more overshoot? See, in the previous case, okay, you must follow it carefully. See, previously without any controller, we have seen that the input was 1 per unit, but the output we are getting of 95% error. Okay, so we have used proportional controller. So proportional controller, what it does, it has too much overshoot, so it increases the magnitude, okay, proportionately to the error, otherwise you will not reach 1. So proportional controller is important. So its gain has to be high, but if it is too high it will overshoot. Okay, so if it is too low it will be less than 1, so it has to be high. Now since it is having overshoot, there is huge time for settling time. It is taking too much time to settle, so that means there is requirements for damping. Okay, so that is why PD controller was used. With the help of PD controller, it reduced the overshoot due to its damping capability, and the settling time reduced. Previously for P controller you can see settling time is 1 second almost, but for PD controller settling time is 0.5 second. But steady state error it was not reached. You cannot reach steady state error. Error is not 0. Now for PI controller is able to make the steady state error 0, PI controller. But if you use 500 the same gain for PI controller, since D controller is not there in PI, because in PI controller we are using proportional controller and integral controller. But if you use proportional controller, what will happen? It will result in huge overshoot. So damping is required. But derivative controller, if you are not implementing, then damping cannot be done. So PI controller means proportional and integral. So integral controller will not help in damping. It will help you to reduce the offset. It will help you to make the error 0, steady state error 0. But damping it cannot provide. That is why, since damping element is not there, the derivative controller is not there. So for PI controller, since proportional gain, if you are using 500 as you have used for PD controller, for PD also we have used KP as 500, but PD controller, the derivative controller, has the capability of reduce the overshoot by implementing damping. So you can see it has damped and the steady state has reached very early. Here only the steady state has reached. Okay, but in PI controller, see, damping capability is not there because of absence of the derivative controller, so the overshoot is high. That is why what we can do in this case, see, the proportional controller magnitude has to be reduced. Okay, because in case of PD controller we were not bothered about magnitude because we know that derivative will damp it. But since integral controller cannot damp it, it can only reduce the offset and make the error 0. So we have to reduce the value of Kp. Now if you reduce the value of Kp, then you see the damping is reduced. So the input is 1, so it has almost reached 1. Okay, and after steady state, see, one thing is problem is there. It has reduced the error. See, error is gone. Error is gone. No gap is there. We can see very few less gap. If I zoom it more and more, see, almost errorless, because see, it is that this line is 0.9995. So I understand it is almost 0. Okay, it is almost 0. If we keep on increasing, see, it is 0.9999 and it is 1. So it is almost 0. In previous case we have seen that there was considerable amount of error. So there was significant error. But in this case there is no error. But one thing is there, that see, the time taking to settle, it took more than 2 seconds to settle. Okay, if I compare PD controller and PI controller now, okay, then you will be able to see that yes, PD controller will not reach the maximum. Okay, let us see for your understanding. If I keep the Kp to be 30, then if I use PD controller, then see, PD controller, it will not reach 1 because Kp is very low, proportional gain is very low. For PD controller, proportional gain has to be high because it will damp it. But integral controller, the integral KD value, Ki value, the integral controller gain has to be little bit considerable amount. So Kp can be low because if you put Kp high, it will not be able to damp it. So Kp should be low. Now see the comparison that PI controller has reduced the error. If you now zoom into the PD controller, see, there is too much error, almost see 96, 98. So quite, it is not 0.0001, it is not like that. It is having some considerable, a significant amount of error. But in this particular case, okay, for KI controller, for the PI controller, error is 0. But see, the PI has taken more than 2 seconds from here. I think it has settled down, but PD controller has settled down less than 1 second because PD controller has very much, you can say, damping capability. So that means if we combine both PI and PD, then what we will get? We will get the advantage of PD controller. What is the advantage of PD controller? settling time less, it will settle down very fast. That means transient state will be gone very fast. So steady state we will get very early. So settling time will be very fast. That is the advantage of PD controller. And advantage of PI controller is that it can give you the steady state error 0. So if you combine both, you will get the effect advantage of both of them. Okay. So we will use PID controller now. Okay. This was the case we have seen. The settling time is very high. Okay, for PI controller. So using integral controller makes the system type 1. Type 1 because you can see one S is being added in the denominator. It has become type 1 system. Okay. A pole at the origin. Okay, so just a comparison. Okay. Now the response shows that integral controller has removed the steady state error and improved the transient response, but it has also increased the system settling time. Okay, so that is why we will use the PID controller. PID controller will give you the best output with the least settling time, with maximum overshoot, maximum damping, and the rise time is also very less, and steady state error to be 0. Okay, so coming to the PID controller, so see PID means all three together added up. So this is the time domain equation. Okay, Kp, Kd and Ki all there. If you find the Laplace transform, so this is the Cs, this transfer function will be Cs, this one is Cs. Okay, so Us by Es, Es is equals to Kp plus Skd plus Kis, Ki by S. So the transfer function will be, open loop transfer function is this one, GSHS, so Kp GSHS open loop transfer function. So we just modify the transfer function, the type 1 system 0. So yes, this is not required. HS is not there. Sorry, there is a mistake over here. HS is not required over here. Okay. So it is called GS actually. So GS and CS. GS and CS. Oh, sorry. In this case, HS should not be written. Rather open loop transfer function. Okay, open loop transfer function in the sense means that it is told that it is not connected over here. So it is CS, PS and HS. The same thing, we will not go by that. We will use our own concept that we have done, that the XS by FS. XS by FS we have already done the way we were doing, is equals to CS PS by 1 plus CS PS. Okay, 1 plus CSPS. Okay, now we will put PS CS this one and PS as we know 1 by S square plus 10s plus 20. So after simplifying we get this entire transfer function. This is the transfer function of the PID controller. Okay, now we will be changing the values or putting the values of the gains. Now we will use Kp 500, Kd as 50 and Ki as 400. Okay. Why 400? Because the error has to be minimized, because this Kd is there. So Kd, what we will do, it will help the damping of the overshoot. So Kp we can keep 500 and Ki should be high, otherwise the error we will not get. Since Kp is high now, because in the previous case, if you can remember, we have seen that if Kp is kept as 500 and Ki to be less 70, then the error is not minimized. Okay, let me show you once again. This is important, so I am showing you step by step so that you can understand. This one. Okay, so if you use 30 and if you use 500, there was a problem. Okay, there was a problem. So the problem was overshoot is there. Okay, so that is why we will use 30 for ki, but once we use kd, so since 500 we can use because it will damp it, so there is no problem. But if you don't increase the value of ki, what will happen? See, for 500 value the error was not 0, so ki, that gain of the integral controller has to be high also. The gain of the integral controller has to be high also, otherwise it will not be able to damp. It will not be able to make the steady state error 0. अगर ki ज्यादा रखते हैं तो एरर 0 नहीं होगा. एरर 0 करने के लिए, सॉरी kp को ज्यादा रखते हैं तो एरर 0 नहीं होगा. एरर को 0 करने के लिए हमको ki का वैल्यू भी ज्यादा रखना पड़ेगा. ठीक है, मान लो क्या अगर यहाँ पर हम लोग 400 रखते हैं, तो देखो एरर 0 हो गया. ठीक है, की का वैल्यू बढ़ाने से एरर 0 हो गया, लेकिन डैम्पिंग था, डैम्पिंग नहीं है, ओवरशूट ज़्यादा है. ठीक है, इसलिए हम केडी को इस्तेमाल करेंगे. केडी को इस्तेमाल करेंगे, सॉरी ये ज़रूरत नहीं है, सॉरी सिर्फ केडी, और ये भी ज़रूरत नहीं है क्योंकि यहाँ पर PID होगा, मतलब कोड PID. Okay, we will hide this. Okay, now we will take this. PID. Okay, now the damping value was kept like this 550. Okay, so पहले क्या करते हैं, पहले इसको कम रखते हैं. मान लो कि जो था पहले 70 30 10 70, देखते क्या होता है. ये देखो सेटलिंग टाइम बढ़ गया बहुत. ठीक है, क्योंकि प्रोपोर्शनल अगर ज्यादा नहीं होगा तो प्रॉब्लम क्या है कि वो ओवरशूट नहीं देगा, मतलब जंप नहीं करेगा. जंप करने से प्रॉब्लम क्या होता है कि ओवरशूट ज्यादा होता है, लेकिन डी कंट्रोलर, डेरिवेटिव कंट्रोलर इसको डैम्प कर देता है. इसलिए जब डेरिवेटिव कंट्रोलर होगा तो इसको हम बढ़ाना चाहिए, नहीं तो ज्यादा डैम्प कर, लेकिन डेरिवेटिव कंट्रोलर पहले डैम्प कर देता है. इसलिए अगर पी कंट्रोलर का मैग्नीट्यूड गेन ज्यादा नहीं होता है, डी जब प्रेजेंट है तब उसको ज्यादा होना चाहिए. अगर डी प्रेजेंट है लेकिन केपी का वैल्यू कम है तो डी क्या करेगा, उसको कम में ही और डैम्प करेगा तो वो ज्यादा कम हो जाएगा. इसलिए व्हेन डी कंट्रोलर इज देयर वी हैव टू इंक्रीज द वैल्यू ऑफ केपी, केडी सॉरी यस केपी. तो इसको बढ़ाना चाहिए, नहीं तो ये डैम्प कर देगा ज्यादा. ठीक है, अभी इसको 500 रखने से क्या होता है देखते हैं. अभी देखो एरर मिनिमाइज नहीं हुआ. क्यों नहीं हुआ? क्योंकि जो मैंने कहा था कि केपी अगर बढ़ा दे तो केआई इसको कम रहेगा तो वो एरर को मिनिमाइज नहीं कर सकता. इसको केआई को बढ़ाना पड़ेगा. दिस हैज टू बी केप इन माइंड. इफ केपी इज हाई then ki has to be high also, otherwise we will not be able to make this test error 0. अब देखो ऑलमोस्ट स्टेडी स्टेट एरर 0 हो रहा है, लेकिन प्रॉब्लम क्या हुआ कि केपी का वैल्यू ज्यादा है तो ज्यादा वो ओवरशूट हो गया. केडी जो है, केडी उसको ज्यादा डैम्प नहीं कर पाया है, इसलिए केडी का वैल्यू थोड़ा बढ़ाना चाहिए ताकि वो डैम्प कर सके. तो केडी का वैल्यू हम 50 रखेंगे तो थोड़ा ज्यादा डैम्प करे. मिनट 500 or not 500, I think it is, yes, 500 50 and 400. 550 400. टाइम बहुत कम दिखा रहा है इसलिए 1 मिनट टाइम को बढ़ा देते हैं, एक्सिस को यहाँ पर ला देते हैं एक्सिस। एक्स एक्सिस रखेंगे हम 0 to 5 सेकेंड्स और वाई एक्सिस रखेंगे 0 to 1.2। अभी देखो, अच्छा एरर अभी 0 नहीं हुआ है ना, मिनट क्या है, क्या वैल्यू थोड़ा बढ़ाना है। कम कर देते थोड़ा, उसको क्रॉस कर गया 1 मिनट। Now you can see that the input was step, okay, output is also almost step, because if you zoom now, this is just tuning of the gains. Zoom now, you can see error is almost gone, okay, see 0.995, then also it is so much high, so that means error is almost gone. So which means that the error which was there, it is totally eliminated, stage error is gone, because it is 0 because of the integral controller, and PI controller, see the value of PI is 500, but the KD has damped it, okay, KD has damped it, but KP is very high, but since KP is very high, KD has damped it, but KI has to be high also, otherwise it will not be able to make the error 0. So this has to be kept in mind, that KD cannot be more than, it cannot be too much, but KI has to be too much. Often in many cases KI may be greater than KP also. Okay. This is just depending upon the tuning. If I tune it in this way, suppose इसको 700 रखते हैं, तो देखो इसका जो है, 1 मिनट, इसको पहले रखने से 500 जब था, तब यहाँ पर जो वैल्यू है राइज कर रहा था ना, राइज टाइम इज लाइक दिस, से इट इज 0.166। इफ आई वांट टू रिड्यूस इट, इसको और भी कम करना है, मान लो कि यहाँ पर लाना है, ठीक है, 0.05 पे लाना है, क्या करेंगे, इसको बढ़ा देंगे 700, ठीक है, इसको बढ़ाएंगे, तो देखो ये जो राइज टाइम हुआ ये और कम हो गया ना, इसको और बढ़ाएंगे, और कम हो गया, इसको और बढ़ाते हैं, 1000 रखते हैं, और कम हो गया। तो मान लो कि मुझे ये इसको टच करना है, तो क्या करेंगे हम लोग, 1500 रखते हैं, देखो पूरा टच करने के जा रहा है, लेकिन ओवरशूट हो गया, तो डैम्पिंग को बढ़ाएंगे, डैम्पिंग को 100 कर दिया मान लो, डैम्पिंग और बनाना है 150, 150 सफिशिएंट है, लेकिन ये भी इसको बढ़ाना है, तो इसको क्या करेंगे, इसको 1500 कर देते हैं, तो एरर नहीं जा रहा है, एरर रह जा रहा है, फिर भी एरर है, इसको 2000 कर देते हैं। ठीक है, अब देखो और भी बेहतर रिजल्ट मिल गया हमको, राइज टाइम जो है वो 0.4 पे चला गया, ठीक है, और भी कम हो गया, और भी थोड़ा सा नीचे है, तो इसको 2200 करते हैं अब। So you can see it is almost unit step input, unit step output, ठीक है, बट प्रॉब्लम इज यू कैन नॉट डू दिस ऑफ आवर ओन, मैटलैब में हम लोग कर सकते हैं, लेकिन अगर एक्चुअल सिस्टम अगर तुम डिजाइन कर रहे हो, पीआईडी कंट्रोलर तुम 1500, 150, 2200 रखोगे तो वो मैनेज नहीं कर पाएगा, बहुत एक्सपेंसिव हो जाएगा, बहुत कॉम्प्लेक्स हो जाएगा, इसलिए फिजिबल रेट रखना है। इट इज नॉट ऑलवेज पॉसिबल टू गेट द डिजायर्ड आउटपुट। मान लो कि ये तो बहुत अच्छा लग रहा है ना देखने में कि राइज टाइम बहुत कम है, लेकिन पॉसिबल नहीं है, क्योंकि थोड़ा कम भी रखना है, नहीं तो सिस्टम को डिजाइन नहीं कर पाएंगे, कॉम्प्लेक्स हो जाएगा। इसलिए पहला जो था थोड़ा ऐसा था कि 500 था, ये था 50 और ये था 1000, तो इसका राइज टाइम थोड़ा सा ज्यादा था, लेकिन सिस्टम स्टेबल हो रहा था, दैट इज सफिशिएंट। ओके, दैट इज वी कैन नॉट इंक्रीज एज मच एज पॉसिबल, we should increase as per requirement, as per permissible, and as per the keeping in mind the cost effectiveness also. Okay, so this is the conclusion. So conclusion, I'm just showing you that thus a PID controller has removed the steady state error and decreased the system settling times while maintaining a reasonable transient response. While designing a PID controller, general rule is to add proportional controller to get the desired rise time, add derivative controller to get the desired overshoot, and then add integral controller to eliminate the steady state error. So rise time, better rise time, that means less rise time will provided by the proportional controller. The less overshoot will be provided by the derivative controller, and the integral controller will help you to eliminate the steady state error. Then there is applications, limitations that you can maybe discuss later, or you can read of your own. Okay, so have you understood the concept of PID controller, why PID is used, and what are the differences between PI, PD, P and PID?
Yes, sir.
Okay, fine. So I will share the notes with you, lab notes as well as the theory notes. Okay, so that if you have MATLAB, you can practice, and so that next class we will start the board plot. Okay, so then thank you, students.
Thank you, sir.
Thank you, sir.